ICMP is Internet Control Message Protocol. Yeah.
Could you explain something from the DHCP example? In the third request, the writing client, he knows the server's IP, right? He knows the DHCP server's IP, right? In the third one.
Yeah, in third one, why doesn't it use the destination address of 2.5, you're saying?
Yeah.
Yeah, I would think that, let's see, I would think that, to me that makes sense, because now that it knows the source address of DSCP, it should just send it to that source address here. Yeah, I have no reason as to why it is going again broadcast. Okay.
Also, what is the comma 68, 67?
I think those are port numbers. So the destination is port 67. Let's see. The destination is port 67. Then it says the source is 68. The destination is 68 here. Now let's see. This is the source. This is 68 port, which is correct. And then it says the source is 68. The destination is 67, which is correct. Yeah, so that is port number. Basically, they are interchanging with the source address. Any other question? Yeah.
When is lifetime measured in hops and when is it measured in seconds?
Oh, okay. So, just like any other thing, we saw the length and everything else, there is no standard unit used throughout IP world. So here it is really seconds. So the lifetime is measured by a clock, and in this case 1 hour later you will lose your address. All right. Only when we talked about the IP routing, even though it is called time to live, the number goes from 0 through 2 raised to 8, which is 256 or something like that. It's the number of hops. All right, that's a misnomer. If somebody had to rename it, they would call it hops to live, not time to live. So that is hops, and this is time. Everywhere else that we mention, it is generally time. So for example, when we do timeout in TCP, that is time in seconds. Everywhere it is time, except for time to live. Any other question? All right. So let's go back to ICMP. ICMP stands for Internet Control Message Protocol. Now generally when we design a protocol nowadays, we design both the control part and the data part together as one protocol. So FTP does not have a control part and a data part separate. It's just part of the FTP protocol. HTTP, same thing, control and data part of the same protocol. But when IP was designed, for some reason, a strange reason, at that time there were no rules and no guidance. So whoever designed it designed two separate protocols, one for forwarding and one for controlling IP. So the IP control part is called ICMP. So this has to be always run with IP, and it provides the feedback from the network. So when IP is not able to do certain things, it sends an ICMP message. And Subho, are you sending an ICMP message or something else?
Sending an email about CSE.
Okay. All right. Okay. So ICMP is used by IP to send error and control messages. So whenever you get an error, it comes through ICMP message, not as an IP message. Okay. And ICMP does not report errors. So sorry, this would be IP. No, sorry, let me see. ICMP uses IP to send its messages, not UDP. All right. So what that means is that ICMP runs on IP. Okay, if you go back to the protocol stack somewhere we had, my God, it's too early. Right here, ICMP runs on IP, not on UDP. Okay. ICP runs on IP. ICMP does not report errors on ICMP message. The question is, if suppose ICMP runs into error, what does it do? Then it forgets it. If IP runs into error, suppose you send an IP packet and it doesn't make it, you will get an ICMP message. But if that ICMP message doesn't get to you, no big deal. That's it, done. And ICMP reports error only on first fragment. So if you have fragmented data, then if you lose 3 fragments out of 5, you will get only 1 error message. And the ICMP header, so it looks like an ICMP header and the data basically. So some part of your packet will be here, not full packet. Some part of the packet will be here, and then the header will be added to that and will be sent back to you in an IP packet. So you will then take that, put it into an IP packet, put an IP header, and then data link header and so on and so forth, and will be sent back to you. And it will be sent back to you from anywhere. So it is not that, so basically it could be multiple hops away where your packet was lost or dropped or whatever, and you will get a message that your packet was dropped. Okay? So that is what ICMP for. Now, let's look at this a little bit more. There is an error code in the ICMP message, and there is a type of message. So the type of message is this type, 1 byte, 8-bit. If it is 0, means it is not an error, it is simply an echo reply. If it is 8, this is an echo request. So you want to send some data to somebody and ask them to echo it back to you, loop back. Then you send an echo request and you get an echo reply. Yeah.
These are all the ICMP header?
These are all the ICMP types and messages. Actually, the messages basically are understood because only type is there, and that means that. Right? 3 means destination unreachable. So if you sent a packet to some place and it didn't make it, it will come back as destination unreachable. Source quench. This will be sent if you send too many packets. You might get a message saying that, hey, you are sending too many, please slow down. That is source quench. Redirect. If you send to router 1 and there are 2 routers on the network, and you send to router 1 and say, please send it to Germany, and they will say, no, hold on, please send it to that router, it's better for you for Germany. So the better path is through that router. So that is a redirect. That is redirect. Redirect means from now on, this one is okay, I will send it. But the next packet, please send it through that router because they have a better path. Time exceeded. This is when your lifetime is exceeded. You have gone through the hops, more hops than you said. So if you send a packet with time to live of 11 and it passes through 11 hops, then it will get time exceeded. You will get an ICMP message which says time exceeded. Parameter unintelligible. So if you put a fragment field or any other field like that, and which has an invalid value for some of the length or type or the offset or something, that you will get that message. Timestamp request and timestamp reply. You can send to somebody and timestamp it, and so that is what the request is. Basically you can send a timestamp request and then the reply will come back with the timestamp. Information request, information reply, address mask request, and address mask reply. So these are all the things that you could ask some other host, and they will reply it back using ICMP. And there are more, by the way. This is not the complete list. All right. So I have explained most of these to you already. Source quench, time exceeded, fragmentation required. So this is what will happen is if you send a fragment, if you send a datagram which is longer than the MTU of some router on the way, and you had set no fragment, please. If you said no fragment, the packet will be dropped and you will get an ICMP message. All right. If you didn't set that bit, then the packet will not be dropped, it will be fragmented and forwarded. Right? But why would you set that bit? Anybody has an idea why would you want to set that bit? Because you don't want that fragmentation to happen on 2000 packets you are going to send next. Right? So you would rather drop the first packet and get the ICMP and then reduce the packet size, so that your other packets will not have the same fate. So that's what is done actually. To find out what is the right MTU for some path, you send a packet with this thing set and you will get a reply back saying that this is. Then you send with that one and then it will go through some routers, and some other router may have even a smaller MTU. Right? You will get another one. So once it makes it through all the way, then you use that for all the packets. Yeah.
In the reply, you get the size, the maximum size of the packet.
Yeah, it says maximum size exceeded, and that's where in one of these codes, parameters, if any, there might be MTU size. All right. Address mask reply. What is the subnet mask on this subnet? And ping. Okay, so ping, you have used ping, all of you have used ping, that uses ICMP echo. Yeah.
For the fragmentation part, you mentioned that different routers could fragment at different times. So what happens if like the third router fragments? Does it get dropped and resent and then it could
No, hold on.
fragment?
Different routers will fragment, means hold on. If you are going on one path, so what I said was that the first router can drop it and says, I cannot take any more than 1000 bytes. Then you send a 1000 byte message, it goes to the first router, but this third router drops it and says, I cannot take any more than 512 bytes. So then you send a 512 message and you keep doing this lower and lower and lower until it reaches the destination.
Okay, so every router has to be.
So that means every router is happy with the size. All right, so ping uses ICMP echo. Ping is exactly that. In the ping, you use the ICMP protocol. And nowadays, many of the firewalls are programmed to stop the ICMP traffic. All right. So, for example, if from your home, I don't know, it might be different from the dorm. From your home, or from my home, for example, if I say ping boostal.edu, no response comes back. Okay, Boostal doesn't respond to pings. Doesn't waste its bandwidth in responding to pings. But if you do Google, it does. If you go to something else, it may not. So everybody has a choice of whether they want to respond to ping to echoes or not. Trace route. Trace route does not use any of these messages. It uses actually TTL expired, which is basically what it does is TTL expired. Where is TTL expired? Time exceeded, number 11. What it does is it sends, trace route sends a message with hop to live equal to 1. What will happen is as soon as it reaches the first router will decrease that to 0 and say, oh, this packet is outlived. It will send back to you a number 11 ICMP saying that I dropped your packet because it exceeded the number of hops you specified. Right? Then it will send a message with 2 hops to live. The second router will drop it and send a message back. Then it will send a message with time to live of 3 hops, and that's how it finds out that the Google is 14 hops away. Yeah.
So is that why when you call it, you see multiple lines show
Yeah. Yeah. All right, each is like a ping in some sense, but yeah, go ahead.
Could you explain again the ICMP messages? There are no fragment bit?
Yeah, no fragment bit part. So one of the flags in IP header is no fragment bit. Let's see, flags. See here it says flags, and then it says for fragmentation and reassembly. Let's see if we have a detail of those flags. Well, we don't have the details in the slides. It might be in the book, but there are many flags there. One of the flag is more fragment flags that we discussed, but there is something called no fragment flag. So what that means is that the routers should not fragment this message. They would rather drop it and send me an ICMP.
Why do they need to send in an ICMP?
So that I can find out what is the smallest MTU on the path. You know, MTU is maximum transmission unit, the maximum IP size packet that will go through without fragmentation. And therefore, if I'm sending large amount of data, I don't want it to be fragmented, every single packet to be fragmented. So, you know, I would rather send smaller data right from home. See what I mean? Yeah.
But this bit just indicates that it's not the last segment. It's not an instruction not to fragment.
Oh no, this is not the flag. Oh no, there is a flag which is missing in this list.
Okay, so there is a no fragmentation.
There is a no fragment flag, yeah. Sorry. All right. So this is section 4.4.3. Any question about ICMP? None. Moving on to trace route, you have already seen, so there is nothing much here. This is part of ICMP. And so these are basically, trace route is not one message. In this case, there were 12 messages that were sent. Right? Everybody agrees with that? Then we go to IPv6. So IPv4 started running out of addresses back in 1990s, about 20 years ago. At that time, we felt that there are no more addresses and we need to change the address size. Several solutions were invited and one solution was selected, and that solution said that we should have 128-byte addresses, 128-bit addresses, 16-byte addresses, and that was a good compromise between some other people who wanted 256, some people wanted 64-bit, and you know, some 32-bit to that size and all that. But anyway, 128-bit address was selected. So IPv6 is this version 6. So what happened to IPv4 and what is IPv6? What happened to IP version 5? Well, there is some IP version 5 somewhere, but nobody is using it, so we don't know anything about it. But there was a version after 4 which didn't get too much currency. So 6 is after 4. And it was argued that 2 raised to 128 is big enough for our lifetime, because 2 raised to 128 is 10 raised to 38 addresses. And if you were to give every single piece of sand an address, you will have 1021 addresses per square meter of the Earth's surface. Okay, so you could have as many devices as you want, right? And obviously they didn't think of something which is not on the Earth. Well, IP can get there, right? So we will run out of that if we go to Mars. But anyway, if assigned at the rate of 10 raised to 6, a million address per microsecond, it will take 20 years for us to assign it. So we can't really get rid of that fast. And since we cannot put it in decimal anymore, so we will use hex. So IPv6 addresses are in hex. And they are 2 bytes at a time. So FEDC colon 00 colon 00, and since they are hex, we use colon. Yeah.
Why can't we still use the birth notation?
Oh, it will be just too many numbers to remember. Can you remember 16 numbers? Can you remember your credit card with only one digit each? 16 digits?
No, but I won't remember.
Exactly. See, good thing is that nobody needs to remember the address. DNS does, but you just remember the name. So this is, they just decided to use hex. And by this time, by the way, we had moved beyond decimal long time ago. This was designed in the old days when they still had decimal computers, let alone binary computers. And this is pretty old. So this is hex, and then they made some shortcuts, and the shortcuts is that if you have leading zeros, you don't have to tell me that I have so many zeros in the beginning, you can just tell me the end. But if you have zeros in the middle, you can skip one sequence. So there are 3 zeros here, 3 whatever it is here, and 2 here. Then you just can say double colon. When you say double colon, means everything else in between is 0, and you can have only one sequence like that. Why one sequence?
It's the only way to reconstruct.
Yeah, the only way to find out how many are missing. Because you know 1, 2, 3, 4, 5 are already specified, so 11 are missing. Sorry, not 11, 8. 8 minus 5 is 3 are missing. Yeah, was there a hand from the back for the same thing? Answer, yeah, good, thank you. And when you see a colon in the beginning, that means the zeros are missing at the front. And in this case, 1, 2, 3, 4. How many zeros are missing? 4. All right, where actually when we say 1 0 means 4 zeros like that. Each is the 4 bits. So this is 16 bit. Yeah, 4 bit, 4 bit, 4 bit, 4 bit. 16 bit times 8 is 128 bit. Can leave the last 32 bit in that decimal notation. So you can write down like this too, colon colon 127.23.45.88, where these are decimal numbers because there are dots here, therefore they are decimal numbers, and they can be, we will figure it out what that means in 128 bit. And then can you specify a prefix by length? So you can say /50, we will take 50 bits out of that. Okay?
The left side?
Yeah?
The 50 is the left, the most left.
Yeah. Prefix is always the left from the beginning. All right. So IPv6. IPv6 header style was changed. The header style is very different from IPv4. Of course, the version number is same. Version number field is same 4 bit, but other than that, everything else is different. So the first field is priority. Then there is something called flow label. Then there is a payload length. So in this case, we had total length, which means the header plus the data. Here, this means only data. Next header. Here there was only one header. Here they had many headers. IPv6 does not have to have one header. It will have more headers. So this will be the pointer to the next header, not pointer, the number of the next header. So it will say the next header is number 16. So that is, we know what 16 number header is. All right, and we will look for that after this thing is done. This header is done. And then number 16 might say, well, the next header is 10. We know what number 10 is, and then we will look for that after that header is over. So it could be a whole sequence of headers. Hop limit. This was called time to live here. That is called now hop limit. Then the source address, which is now 128 bit, 4 bytes, 4 32 bit words. Here it is only one word. Destination address, which is 4 32 bit words and one word. And so this is the main header actually. There is more to come. Everybody understood this main header? Yeah.
So a general question about the number of IP addresses we need. It's not per device, it's per link that those devices are connected to. Is that correct?
Okay. The question is how many addresses we need. Suppose we have let me think of an example. Suppose we have 3 devices and they are connected by maybe 3 is not a good number, 4. Suppose we have 4 devices and they are connected by 6 links. Yeah, this is only 2 of them. So this is the most visible one. So how many addresses do you need? The question was, do you need per link a different address, or do you need per device? So let me just do a survey. So one answer is 12. Okay. Anybody with a different answer? Everybody has 12? 4. Anybody has a different answer?
Is there an analog?
Huh?
I think like it depends, but it could be 4 or it could be 1. Yeah.
Actually, the right answer is 12. Each of these need an address.
Can
You
you
see?
need the same address though?
No. See, the thing is, the reason you cannot use the same address is because when you want to reach this from here, you have to go like that. When you want to reach, you have a direct path.
Can you explain that again?
Okay. So you want to go from A to B.
Okay.
So what is the B's address that you will use? If you use this one, you will go like that. If you use this address, you will have to go. You will go in like that, right?
But if they're the same address,
It will be very confusing because it's a good question. Let me think about it for a minute. You see, what you are talking about is like this. Something like this, I think. Let me see. See, the thing is, you need 3 interfaces here. Because you have 3 links, you need 3 interfaces. And so actually, this is not possible. Basically, you need 3 addresses because even though we call them IP address or the host address, they are not really host address, they are interface address. And in Mac, they are called IF address, IF config or whatever. In Mac you have to say IF config instead of IP config, that interface configuration. And so this is really the interface address, this is interface address, this is interface address. And yeah, it's confusing, but that is really the thing, is that you have 3 interfaces there.
So does that mean we have 2 IP addresses that are connected up with wired and wireless?
Oh yeah, of course. You should check that out. You know how do you check it out? Just do IP config on your laptop and you will see 2 addresses. Yeah.
I think his question might have been though, if they're all behind private, they're all on private addresses.
Yeah.
The total number of IP addresses can be public. Ours is limited by the number of networks.
Oh, okay. So let me answer. That's a different question. The question was, if you have private addresses, then you don't need that many public addresses. The answer is yes, but this question was raised before we knew about the private addresses. This is IPv6 was designed in 1990s, before we knew the private addresses. So what happened was that we ran out of addresses and we started thinking about the ways, and the first simplest way that came is that we make a bigger address, right? So IPv6 came about. As soon as IPv6 came out, people said, no, that is too much. You can just do it with this. So other solutions were proposed. And those solutions, one of those solutions is private addresses. All right? And those solutions succeeded wildly while IPv6 failed wildly. So basically that's why IPv6 did not take off, because those other solutions made the problem go away. So the private addresses really made the problem go away.
So back then, if you wanted an internet connection, you
Everybody had only public address. That was the only thing we knew.
And is this used at all today?
Oh, this is used a lot in China. I mean, you don't have an alternative there. I mean, think about it. I have told you about, right? So in Europe, in China, in any other country you go, you need IPv6 because they don't have enough IPv4 addresses.
How many does IP4 give you?
Huh? 2 raised to 32. Yeah, which is 4 billion or something, and we have 6 billion people. I mean, it's not enough to cover the people, let alone devices. Each person has dozens of devices. Okay, so everybody understand now IPv6 need for it and why the solution was invented, and the fact that there are multiple headers. I haven't talked about multiple headers. So first thing is that IPv6 is different from IPv4 because it is 1995, not 1975. The header size, they said we don't need to put everything in the header, so they had the main header is only twice the size. So this length is 4 plus 4 plus 2, 10 times 32 bits, and this is probably 5 times 32 bits. So only twice. Only version number has the same position and meaning, everything else is different. They removed the header length, they removed the type of service, they removed identification, flags, fragment, blah blah, everything is removed. And that means no fragmentation. So IPv6 does not allow fragmentation. Period. Data length replaced by payload length, protocol type replaced by next header. So in the previous one we had a protocol type where we will say in the next header is TCP, because obviously you don't have IP, you could have IP inside IP, but generally inside IP you will have TCP or UDP. So this will have the protocol number for that. Hold on. But now here, before the TCP comes, you might have some other IPv6 headers. They have a number too. All right? Go ahead, question.
Yeah, why did they remove fragmentation?
Because they felt that there was too much waste of time of the routers, and therefore the only way to send the packet would be that you first find out what is the MTU and then send that.
So you always get ICMP if you send.
You will get an ICMP. Basically, you send a packet and then you will get an ICMP, and then. All right.
There's no fragment.
So basically, no fragment bit is set by default. All right. Protocol type file, next header, time to live replaced by half limit, so they wanted to be truthful, and they added priority and the flow label. So they added priority. There was no priority before. Before they had actually something similar which was called type of service, 4 bits, now they call it priority, and flow label. So what is a flow label? Basically, by this time, by 1995, we started realizing that many packets are related. And so if the many packets belong to the same application, maybe they should get the same treatment, they should get the same priority, they should get this, whatever, quality of service. So we put a number which is say this is the flow number 15, this is the flow number 17. So when the application sends or the source sends the packet, it puts the flow label, and then the routers treat that whole flow as one, basically with the same quality of service. So the flow label field was put. Yeah, question now.
After I get the ICMP message which says this is too big for the wire, who divides it? I mean, I still need to divide it to send different packets, right?
No, the source will source.
Like which network there?
Oh, this is only a network layer, layer 3. Layer 3. All right, so, and then flow level now, all fixed size field, and no, there are no variable size fields, like before where you had options and other things, no optional field, but you have optional headers. So whole set of fields are optional together. 8-bit hop limit. So the hop limit is 255, which was actually before, and people would say, why didn't you increase that? Well, by that time it was understood that really the number of hops doesn't go up as the number of devices goes up. You could have now, instead of 4 billion, you might have 4 trillion or 4 whatever quadrillion devices, but the number of hops will still remain limited, 255. The next header field For example, 6 means TCP and 17 means UDP. So that is the protocol number for TCP, this is the protocol number for UDP, 17. If that field says 6, that means the next header is TCP, right? But before it says 6, it will say something else for IPv6 headers. So IPv6 headers, let's see them for a minute. We will talk about them in a minute. But one of the problems that they made a mistake on is this whole transition strategy. They did not really think about as to how the world will transition to 6. And the answer was very academic answer. Very academic answer, which said that the routers will implement both IPv4 and IPv6, which sounds good in the university, but doesn't sound good when you go to buy a router and they say, well, you have to pay for twice as much. So dual stack means each IPv6 router will also implement IPv4, and IPv6 is used if the source host, destination host, and all routers on the path are IPv6 aware. So here's the thing, if you want to use IPv6, everybody has to know IPv6. If you go into your computer, regardless of what computer you have today, you have IPv6 in your computer. Microsoft has implemented it, Apple has implemented it, Linux has implemented it. So there you go. Everybody has implemented it, but routers have not. And if some routers have implemented it maybe in China, but maybe not here. If here some implemented it, maybe one is not implemented. If one has not implemented it, then nobody can go through. Right? So there is no such thing that the whole world will change one day to IPv6. It has to go gradually. And that gradually it cannot happen. Right? That's why in 21 years there is no IPv6.
How does it work? Like, say I send an IPv6 packet, and like the next router supports it, but then he doesn't know where to send it because
You'll drop it.
they drops it.
Yeah. So the thing is, it does work in those countries where it is being used.
Yeah.
But as soon as you get out those countries, you need to get back onto IPv4.
I just saw the slide and thought maybe it converts it.
Yeah. So you can do the tunneling. So that's another answer. So the next answer is tunneling. Tunneling means that you really don't, you put a packet inside a packet. You take your IPv6 packet, complete packet, including the header, and put it inside an IPv4 packet. And then you send it where IPv4 ends. So this is IPv4 land, this is IPv6 land, this is IPv6 land. If you want to go through IPv4, you dig a tunnel. That means you basically put this packet here, it goes from this router to that router, B to E.
How does B know he's IP?
Well, B knows that I speak IPv4 because it speaks IPv4. Even though it is speaking IPv6, it also speaks IPv4 because it is talking to an IPv4 router.
I'm just asking, how does he know he's IP?
Yeah, so every router knows the network configuration, and they know exactly where everybody is and what they speak. So this router knows that the maximum I can go, and I want to go to D, by the way. B knows that I want to go to D, and therefore the maximum I can go on B4 is E.
So what happens is you send an IPv6 packet.
Yeah, it starts from IPv6 here, IPv6 here,
Then
it becomes
makes it
IPv4.
IPv4.
Yeah.
He knows E's IP address, so it sends it over
To E.
IPv4.
E opens the packet,
Opens the packet, gets IPv6, and
sends it on. Yeah. Tunneling is clear. Another name for tunneling is encapsulation. Yeah, go ahead.
So each router knows the configuration because of that Ethernet broadcast?
Okay, so each router knows at least the same protocol routers. I mean, each IPv4 should know all other IPv4 routers, right? And towards the end of this lecture, this chapter, we describe as to how they exchange all this information and they find out. So routing is, we haven't covered routing yet. We are still talking forwarding, right? So how to make the routing table and how to find out who is where and all that, we will talk about that. All right, but key point here is tunneling. Everybody understands tunneling. What is tunneling? Encapsulation. Packet inside a packet. Understood? Okay. All right. So that is the end of IP. And the key points to review are that IPv4 uses 32-bit addresses, which now into two parts. One is the subnet part and one is the host part. Subnet part is no longer fixed. In the beginning, it used to be fixed 8-bit, 16-bit, 32-bit, 24-bit, and we call them ABC classes. But now we have CEDAR. CEDAR means classless, class independent or something like that, right? Routing. So that means we don't have any more ABC, we can have any number of bits. Private addresses can be reused, and private addresses can be reused and help solve the problem to a great extent. ICMP is the IP control protocol for the error message that we discussed today. We discussed DSCP to automatically assign the addresses, and IPv6 uses 128-bit addresses, but it requires dual stack or tunneling to coexist with IPv4. Any questions? Now, there is one question that I want to answer from last time. Somebody said, what about 169 something? Remember? Okay, so the book doesn't have it, so I didn't talk about it, but I will put that in my slides. and I want to explain to you right now without the slide. So there are private addresses, but when IP I think it's dead. I don't know, this doesn't last the 3 hours that I am here in this room. When IPv6 was discovered or was designed, by that time we were much more intelligent about networking, and so a new class of addresses was discovered or put into IPv6 called link local. The idea of the local addresses was slightly different than private addresses. The local address was that if you have an Ethernet link, then any host on that could talk to each other by using link local addresses. Those addresses cannot get out of the link, but they can talk to each other using that address. Okay, for example, inside your home, your mom calls you something and you call your mom something. So you can call your mom, but you cannot send a packet outside of your home addressed to mom, right? It has to be addressed to Mrs. So-and-so with full last name. So inside the link, you can use some special addresses that are good only inside the link. Just like private addresses cannot get out of private network, the link local addresses cannot get out of the link. Then they also had site local. Site local means they can stay in one campus. They cannot go to medical campus. Then they had a organization local or something like that, enterprise local, I forget the name. So they will not get out of Worcester if they want to get out. That is like a private address anyway. So they had many local addresses. So the link local addresses concept was then taken back into IPv4, and a set of addresses were reserved for link local use, and that is 169. Now I forget the exact number, but let's just for the time being take that is 169.0.0, so 169/8, and I could be wrong on that one. Okay, so that address range is reserved that anybody can use. So if you put a Ethernet thing together and you don't have a DSCP server and you put 4 computers on it, they can assign it themselves. All right, and they can talk to each other without DSCP server, but they cannot talk to anybody outside. You understand? And so that was the purpose of that address. Now there is a problem with that link. That out of that, 512 addresses were taken out. So first 256 addresses are reserved for future use, and the last 256 addresses are reserved for future use. So the range is not exactly this, The range is minus the first 256 and the minus the last 256, to be confusing. But anyway, the way you assign that address to yourself is that you select any random number in that range, and then you say, this is my address, and you send a packet to yourself. If you, actually there is another protocol which is used, ARP or something like that, and if nobody else has that address, then you are all set, you can use it. If somebody else has that address, then you select another random number. So by this method, any network can be started without having a DHCP server. Link local address. Okay? So I will prepare a slide on link local, and that will have exact details of this, but that is one thing that we missed in our lecture so far. Any other question? If not, then we move on to routing. So routing, will talk about 4 things. Graph. Maybe I should throw away this one. Every time I use that one, so I'm not going to throw it away either. Graph abstraction. Then we'll talk about the distance vector versus link state, the extras, and Bellman-Ford. Right now it means nothing, none of these. So let's start with this. First of all, is it routing or routing? Right? Routing. Routing is what they do at football games, and the pigs tuffle on the trees and all that, and routing is what we are doing. Routing is what one creates a beveled edge on a table. Have you seen a router? Many people have a router at home. And when you send a corpse of infantrymen into full scale disorganized retreat. So that is what the routing is. So this is routing. The next question is it routing or routing? What is the correct spelling? Well, it depends. It depends whether British or American, and that's why the Oxford dictionary is so thicker, than the American English, because they just use extra letters where none required, right? Many places. So the right spelling is routing, at least for us. With that introduction, let's go to graph abstraction. So from now on, we will look at the networks as a graph. Every node or router is a node in this graph, and there are links which have weights on them, which is somehow related to the cost of the link. What is the cost of the link? Cost of the link would be just the opposite of the speed of the link. So if you have 2 links, one is 1 megabit and one is 10 megabit, 10 megabit is cheaper, will be considered cheaper because it is better for you. Given the choice, you will suddenly take 10 megabit, right? So somehow you make up a cost from the speed, or it could be real cost. It's that you have to pay to AT&T for that link. So anyway, so you make up the cost, then it becomes a very theoretical problem as to what is the shortest cost path from A to B. All right. So now the rest of this lecture is into that kind of mathematics, is trying to find the shortest cost path. All right. So here is a link, here is a network, and here are the costs. Now the costs don't have to be symmetrical. So for example, the cost from going to V to X could be different than going from X to V. And in general they are. For example, when you get a DSL connection, the uplink and the downlinks are always different speeds by design. Okay, so the costs are not the same for uplink and downlink. Downloading 1 megabit is not the same thing as uploading 1 megabit. Uploading 1 megabit is a lot of information, a lot of money. Okay, and that is an extension that one can do, and we will not go into that extension in this course. So we will assume the symmetric links. And so the links are noted by 2 nodes. And again, that is a specialization. For example, U and X could be connected by 2 different links, and we are not going to consider that case here. We are just going to consider one link. So here we have U to V, U to X, V to X, and so on and so forth. These are the links. These are the edges, E. And this is the nodes, N. 6 nodes and 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. Each edge or link has a cast. So for example, W to Z, the cast is 5. And the routing algorithm's job is to find the least cost path. And we are limiting it to undirected graphs. Undirected means we are not going to consider where you can only go one way and not two way. And there are lots of one way streets, but we will not consider them here. All right, and the cost is same, and not only they are undirected but also symmetrical. Simple things. So there are two ways to get this information. One is called distance vector and other is called link state. So two ways. First is that, now here's the thing, before we can find the shortest path, I need to know the complete description of all the nodes and the links in between them. And you need to know, everybody needs to know. But how do you know what is the distance between, what is the link connecting Kansas with whatever city next to that is, right? Kansas has to tell us, right? So the idea is that everybody tells everybody about the links that they are connected to, and then everybody gets the whole picture, and then they do some algorithm to find the shortest path, right? So there are two ways to do it. One is that I could tell the world about my neighbors. So there are 60 people in this room, that is the world. But I have only 5 neighbors, 5 people who are just next to me. I could tell the world about 5 people, and if everybody did that, then everybody will know about everybody, right? Second option is that I could somehow get the information about all 60 people and tell it to these 5 people. All right, so I could tell about the world to my neighbors. All right, so those are the two options. Tell the world about the neighbors or tell the neighbors about the world. All right. When I tell to the neighbors about the world, tell the world to the neighbors, tell about the world to the neighbors, then my information is going to be very big. I have to tell about 60 different nodes to 5 people, right? So it will be big vectors. So, right, that is called distance vector. On the other hand, when I tell the world about my neighbors, I will just tell about the 5 links that I have, that is called link state. Understood? So there are two methods, link state and distance vector. Originally we started with distance vector and now we are moving to link state. Okay? If you look at the old routing algorithms, they were distance vector. The new routing algorithms are link state. And the way to remember them is that the distance vectors are big. Means we are telling about the world to the neighbors, to a small number of people. Whereas the link states are small, we are telling about the small number of people to the world. The traffic is the same, by the way, because if I have to tell 60 people about 5, it is 60 times 5. You know, each vector is 5 long and then 60 messages has to be sent. Or if I have to tell about 60 people to 5, you know, it's almost similar, but there is a difference at the end, as we'll see. So, yeah, question.
How do you know all the people to send in, like, 5 neighbors?
Well, so how do you know what 60 people? Basically, the way it happens is somehow, you know, when the network was started, there were only 2 of us and we knew each other, and then the third person came in, then I tell them about the 2 people we have. And slowly, so basically that somehow when somebody comes in or goes out, then we already know the world, right? Most of the time. All right. So those are the 2 methods. So this is used in the older protocol called RIP. RIP is Routing Information Protocol. And the new routing protocol is called OSPF, Open Link State, whatever. So these are the 2 we will talk about. And there are two algorithms. Now this was a very interesting topic for the mathematicians in computer science. And so Dijkstra, well-known guy, he invented an algorithm for shortest path, and that is called Dijkstra's algorithm. And again, this has to be listened very carefully, because this is in the homework of course, but this is always in the exam. In the exam, if we have an exam on routing, we have to ask about Dijkstra's algorithm and the next one. All right, so listen carefully. So our goal is to find the least cost path, right? And the notation is that each link has a cost from I to j, Cij, and dk is the total path cost from s to k. All right, s is not given. When we say dk, which means the cost, total cost to k, and s is basically me, source. N prime is the set of nodes for which the least cost path is known. So if we have 60 people, I may not know the least cost path to all 60, I may know only 5 or 3 or 7. Those are in N prime. So in the beginning, N prime is just me. Okay, and I had to stop here because I should put the word you here, cost from you, because me, I am you. Okay, I am you. So right now I know the cost only from myself to me, to myself, and then I know the cost to my neighbors, because 5 people I have paid for that link. So I know the cost from me to all my neighbors, and we repeat it. For until I know the cost to everybody. First, right now I don't know the cost to everybody. I know myself. I know the cost to my neighbors, but I don't know whether that is the shortest path or not. And so right now my set of known nodes includes only me. So how we add somebody to that set? We find out what is the minimum among the known next hops. Okay, and whoever is the minimum, that comes inside this set N prime, and the cost table is changed.
How do you know what do you look for?
So first I start with myself. I know the cost to myself is 0, so I am in the set. But then I have 5 neighbors. Then I find out what is the cost to the first neighbor, 2, second neighbor 1, third neighbor 5, 7, 3. So the minimum is 1. So then the 1 comes into the known set. So I know that there is no possibility of getting anywhere without going through him.
Cost link that gets out of
the part that we know. And then now that I have put him into the set, now we have a 2 node set. We will have to find out how can we get out of this set. So I have to find out
the least cost link out of N prime.
of that at that set N prime. Yeah. So let's do it in a tabular form. Basically, the best way to do this is in a tabular form. We start with the first row. On the first row, we write down 0 hops away from me is you, and then we write down the cost to everybody that we know. So the cost to V from you is 2. So we write down the number 2, and the path to V would be U dash V. We will just go like that. Cost to W is 5, and the path would be UW. Cost to X is 1, and the path is UX. Cost to Y is infinity, we don't know, and the path we don't know. Cost to Z we don't know, and the path we don't know. First row, everybody can write the first row? Alright, once you can write the first row, then we find out the minimum in this row. Minimum cost is 1. So we take that one in this set. So now we put X into this set, and that one is, now we will not write anymore here anything. We know how to get to X. There is no better way possible. Now we see, if we know U and X, how can we get to V? Alright. So now the cost to V, if I go through X, it is 3. If I go directly, it is 2. right? So I write down the cast is 2 and the path is UV direct. For W, if I go this way it is 5, if I go that way it is 5, so we UXW, UXW, yeah, right. So we can get 4, so we say the cast is 4 and the path is UXW. And then we have to skip X and we go to Y, we can get to Y by X and the cast is 2, UXY. Z we cannot get right now, so we leave it there. What is the minimum along this set? There are two minimums, either we take V or we take Y, right? It doesn't matter. You can take either one first and the next one will come in the next line. So let's say we arbitrarily selected Y to come into this set. Alright? So everybody knows how to write the second line, second row. So once you write the second row, now you can put the Y in this set. Now we do the same thing, U, X and Y, and we can U, X and Y. These are the three nodes in our set. Can we get to V? Yeah, we can get to V 3 or 2. So we leave it 2 here. W, U, X and Y, we can get to W by this method, 3, cast becomes 3 and the path becomes U, X, Y, W. And then we leave X and Y and then we go to Z. Now we can get to Z and the cast is 4, U, X, Y, Z. So everybody knows how to write this row number which is labeled 2 here, right? Okay. Keep going like that. So now what is the minimum? Obviously the minimum is V. So we just put V into this set, U, X, Y, V. U, X, Y, V. These 4 are in the set. Now we don't have to worry about these 4, we just have to worry about the remaining thing, which are only 2, W and Z. So how can we get to W from this set? Well, you calculate all possible ways and actually you just have to calculate with respect to whatever the new thing came in. So the new came in V, so let's see, that method would be 5 and so that doesn't decrease anything, so that doesn't change anything. So basically 3 remains the cast and the path remains the same. For Z, now we have U, X, W, V. For Z, we don't know still because we don't know cast to W, we know cast to W, U, V, X, Y. So basically this will remain 4 because W is not still in this set. So anyway, now the minimum is 4. Once the W, so 3 comes in, W comes in, and then the Z comes in. So anyway, so these red numbers are what the shortest path are. Shortest path to X is UX, shortest path to Y is UXY, shortest path to V is UV, shortest path to W is UXYW, and so on. All right. Make sure that you understand this. I can do it all over again, all right, because this is one of the key things in networking. Let me start one more time, just to be sure. First we start with 0 hop paths. This is 1 hop path, these are 2 hop paths, these are 3 hop paths, 4 hops, and so on and so forth. In 0 hop paths, only thing we know ourselves, U. Right? Now I am calculating all the shortest path from U. I could give you the same problem as a homework and say please calculate all the paths from X. Right? Then you will have to do the same thing. You will put X in the set and write down the cast to all its neighbors. Then find out the smallest one there, put that into the set and write down the cast. Then find the smallest in there and so on and so forth. Yeah.
If you have 2 paths that are the same length, like tied for the smallest, do you have to do both of them or do you just pick one?
You can just pick one. It doesn't matter. So let's see if there was a case. For example, here, this doesn't happen to be the shortest path, but this is 5 and this is 5. Right? U to W. You could have taken any one. It just so happened that 1 to 4 is cheaper. I mean, 1 UXV is 4. So we took 4 in this example. But if this was not there, this link was not there, then we would have taken either one. Any other question? Everybody feels comfortable for the next homework? Let's see if there is a next homework right here. No, not yet. Let's see where is the next homework. Okay, we have a few more slides to go. So a competing algorithm is called Bellman-Ford algorithm, and the Bellman-Ford algorithm starts slightly differently. In this case, we need to find out the cost of h hop path from u to some node n or x, and that cost is d sub u n of n, which is infinity in the beginning, but as every hop we try to find out what is the minimum. So basically the idea is to find out what is the minimum 1 hop cost to every node, what is the minimum 2 hop cost, what is the minimum 3 hop cost, and so on and so forth. So we go hop by hop. Let's look at the table. Basically, first let's start with a simple example here. X, Y, and Z. X, Y, and actually we need 5 minutes. This is 5 minutes left. Yeah, all right. So I would stop right here. Actually, I will start the Bellman-Ford next time. You need to pick up your password and try out your ONL.
Is there no homework 4D?
Homework. The next homework is not due yet. I mean, whatever the next one is, it's not due. 4E is not due. Oh, 4D is missing, yeah. So I took it out. Sorry, I took it out. So it's not due.
So